Here we discuss the solution of a problem that is given in a JEE examination. The problem is about the domain of a function. The given function is the quotient of two inverse trigonometric functions. This question has appeared in JEE main exam held on 22nd July 2021 in the afternoon shift. The given problem is, if the domain of the function f of x is equal to the quotient of two inverse trigonometric functions, the numerator is cos inverse under the square root of x square minus x plus 1 by the denominator under the square root of sine inverse 2x minus 1 by 2 is the interval semi-open interval alpha to beta, open at alpha end, closed at beta end, then alpha plus beta is equal to. The four options are given to us. Solution. It is known that the domain D of y is equal to under the square root of g of x is given by D is equal to the set of all those real numbers at which g of x greater than or equal to 0. We also know the domain of sine inverse x is the closed and bounded interval minus 1 to plus 1, and the domain of cos inverse x is also the closed and bounded interval minus 1 to plus 1. First, we will find the domain of the numerator. Let d1 is equal to the domain of cos inverse under the square root of x square minus x plus 1. Note that x square minus x plus 1 is equal to x minus 1 by 2 whole square, adjust the terms, plus 3 by 4 will be greater than 0 for all x belongs to R, because it's the sums of the squares. Its minimum value is 3 by 4, and that is why it gives greater than 0 for all x belongs to R. D1 is equal to the set of all those x belongs to R such that x square minus x plus 1 greater than or equal to 0, because it is under the square root. Intersection, set of all those x belongs to R such that minus 1 less than or equal to under the square root of x square minus x plus 1 is less than or equal to 1, because the domain of cos inverse is the closed and bounded interval minus 1 to plus 1. Now the first bracket is the whole of R, because the x square minus x plus 1 is greater than 0 for all x belongs to R. Therefore, the first bracket is R. Intersection. The second bracket is x belongs to R. 0 such that 0 less than or equal to under the square root of x square minus x plus 1 less than or equal to 1. Why? Because note that under the square root of x square minus x plus 1 will give value always greater than 1 for all x belongs to the semi-closed interval minus 1 to 0, closed at minus 1 and open at 0 end. That is why that portion minus 1 to 0 is taken out, because the value is less than or equal to 1, whereas that value is greater than 1. That portion is taken out. So it is the set of all those x belongs to R, 0 less than or equal to under the square root of x square minus x plus 1 less than or equal to 1. It is equal to the set of all x belongs to R such that x square minus x plus 1 less than or equal to 1, for obvious reasons, is equal to the set of all x belongs to R. 1 cancels, x into x minus 1 less than or equal to 0, and that will give you the set of all those x belongs to R such that 0 less than or equal to x less than or equal to 1, and that is the closed and bounded interval 0 to 1. So that is the closed and bounded interval 0 to 1 is the domain of the numerator. Let us now find the D2, the domain of the denominator, that is under the square root of sine inverse of 2x minus 1 by 2. Now, this is the set of all those x belongs to R. Sine inverse of 2x minus 1 by 2 is greater than or equal to 0 because it is under the square root. I know that this under the square root of sine inverse 2x minus 1 by 2 is placed in the denominator. I have to take greater than only, but not equal to. But first I will find d2, then afterwards I will remove that. It is, and the intersection, the set of all those x belongs to R, minus 1 less than or equal to 2x minus 1 by 2 less than or equal to 1, because the uh, domain of sine inverse is closed and bounded interval minus 1 to plus 1. So this is the set of all x belongs to R, 0 less than or equal to sine inverse, and the maximum value of this sine inverse is pi by 2, pi by 2. So the value of sine inverse of is maximum value is pi by 2. That is why it is less than or equal to pi by 2 is intersection the same function I have written, because there is the same function coming here. So I will wait what happens in the first. And it is the set of all those x belongs to R, 0 less than or equal to 2x minus 1 by 2 less than or equal to sine of pi by 2, that is 1. Intersection this second bracket. And now this is the same function, 2x minus 1 by 2 is the same function. So the intersection is the common portion. The common portion is the first bracket. This is the first bracket. Now multiply throughout by 2. The inequality is not get disturbed because 2 is greater than 0. And add 1 throughout, we'll get 1 less than or equal to 2x less than or equal to 3, and divide throughout by 2, and that will be the closed and bounded interval 1 by 2 to 3 by 2. So since this under the square root of sine inverse of 2x minus 1 by 2 is in the denominator, we take d2 star, d2 star is equal to the first bracket as it is, but it is greater than 0, intersection the second bracket as it is. Then the answer what you are going to get is the open 1 by 2 to 3 by 2 closed. Now the domain of f of x is d1, the domain of the numerator intersection, the domain of the denominator d2 star, and that is equal to the d1 is the closed and bounded until 0 to 1 intersection 1 by 2 to 3 by 2 interval open at 1 by 2 and closed at 3 by 2, and intersection is the semi-open interval 1 by 2 to 1, open at 1 by 2 and closed at 1, and it is given semi open interval alpha beta open at alpha end closed at beta end, and alpha will be the 1 by 2, beta is 1, and what is asked is alpha plus beta, that is 1 by 2 plus 1, that is 3 by 2. Let's look at our options, and our answer 3 by 2 appears against the option 4. Therefore our answer is option 4. So that is the discussion of finding the domain of a function, which is the uh, quotient of two inverse trigonometric functions. I hope that you have understood the solution and the method of finding the domain, and I wish you all the best. Thank you.